Finally, we will talk about the metallic bond. When we look at the periodic table, we see that most elements are metals. So what are the characteristic features of metals? They have high electrical conductivity, they have high mechanical strength, and they have high flexibility. Now, uh, when we look at the crystal structure of the metals, we see that the electrons, the valence electrons are released to the lattice as conduction electrons. They are capable to move within the crystal. At zero temperature, they're very loosely bound to isolated atoms. So as soon as we form a crystal, these electrons are released to the crystal structure. Now, the crystal consists of ions dispersed in the sea of free electrons. So they are nearly free actually because they also see the potential due to the potential was due to the core of the atoms, but they're mostly free to move in the lattice. Now, what drives this metallic bond? Well, according to Heisenberg's principle, the uncertainty in position and momentum product is greater or equal to a reduced Planck constant divided by 2. So if you compare the free atom with the isolated atom, with the atom in the crystal, in the free atom, the valence electrons are restricted to a small volume, and that makes the delta P very large. So delta X is small, delta P becomes very large, so they have high kinetic energy. So when you look at the total energy of the electrons, this is going to create an undesirable situation. When we form the crystal structure, they're free to move in a very large volume. So this means that delta X is large, so delta Px becomes small, so the kinetic energy is reduced, and therefore the total energy of the system is reduced. So minimization of energy requirement basically tells us that the electrons, valence electrons being released to the lattice according to Heisenberg's principle is quantum mechanically desirable because these free electrons will on average have a kinetic energy that is much lower than the electrons that are bound to the atom. And these electrons will act as a glue that holds the ions together. So this is basically the metallic bond. Now, when we compare the metallic bond with other bonds, in ionic bond, we see a much stronger bonds. Bonding is generally weaker. And how do we get this information? Well, if you look at the sodium metal and sodium chloride structure, in sodium metal, the melting temperature is 400 degrees Celsius. The sodium chloride melting temperature is 1100 degrees Celsius, which means it's a lot harder to break the bonds in the sodium chloride. So when we look at transition metals like iron, nickel, cobalt, titanium, etc., in addition to these free electrons, we have more localized 3D electrons, and they tend to create covalent bonds with the nearest neighbors. And how do we obtain these covalent bonds? We have discussed covalent bonds in the previous video. Here we have, instead of sp, SD hybridization. So this leads to bonding strengths comparable to ionic bonds. So the bonding in transition metals is quite strong, not due to the metallic bond, but due to the accompanying covalent bond due to SD hybridization. So there are two figures of merit we look at to decide if there's going to be an ionic bond. That's the first one is electronegativity. That's the ability of an atom to attract electrons. So the sodium provides this electron to the lattice to form the metallic bond, so it has low electronegativity. So for an element in its crystal structure to form metallic bond, it has to have low electronegativity like sodium. Electron affinity, on the other hand, is the energy released when an atom accepts an electron. So this is X plus an electron becomes X minus ionized plus the energy released. That's electron affinity. So positive electron affinity for an atom implies that it is an electron acceptor. So we have electronegativity, the ability of an atom to attract electrons. That means to release electrons to the lattice so that you can attract electrons, and electron affinity is the amount of energy released when an atom accepts an electron to become ionized, negatively charged. Now, having talked about these models, well, these bonds, one thing we have considered is that the atoms in the lattice are static, they're not moving at all. So we have several experimental facts that are suggesting otherwise. For example, X-ray scattering. We have the von Laue diffraction condition and Bragg diffraction condition. So we have an expectation from the static lattice model that there won't be any intensity in the scattered X-ray radiation in certain directions. However, we find that there is a background of scattered X-ray radiation even in directions that are not allowed by the Bragg condition. On the other hand, the transmission of sound. Sound can be transmitted through crystals, especially insulators with no conduction electrons. However, if the atoms were not moving at all, how can sound propagate in the crystal? This requires vibrational waves in the lattice of ions. So the static model would suggest that all crystals are acoustic insulators, but that's not the case. Even insulators are transmitting sound. Thermal conductivity. So in metals, we can say that the temperature, the heat is transported through conduction electrons, but however, in insulators, we also see that heat is transmitted, and they have too few electrons to do this job, and that could be only due to vibrational motion of the atoms, so that's due to lattice degrees of freedom. And the fact that we have melting at sufficiently high temperatures suggests that the ions will leave their equilibrium positions and wander great distances through the resulting liquid. And this can only be explained by the gradual increase in the amplitude of lattice vibrations with temperature, which eventually leads to breaking of the bonds. Thermal expansion, on the other hand, in the static model of the lattice, the atoms don't move at all, but when we increase the temperature, temperature will increase the number of conduction electrons in the static model, but we see that even in insulators, they expand with increasing temperature. That means the bond lengths are changing, so the atoms are not at rest at their positions, they are moving. And finally, we can talk about superconductivity. Below a critical temperature, the resistivity of certain metals drops to zero. And this has been attributed to the interaction of two electrons that are called Cooper pairs, which are going through the lattice, and the interaction between the Cooper pairs is mediated through lattice vibration. So superconductivity would not exist if the static model was correct.